In this video, I want to talk about normal subgroups. And in order to define a normal subgroup, I need to start by defining a conjugate. Let's let A be an element of G, which is our given group. So we have some fixed element of our group. A conjugate of A is any element of this form XA X inverse, where X is another element of the group. So as an example, if we consider our star, so the group of real numbers under multiplication, and I'm going to pick the element 2, some conjugates of 2 would be something like 1/3 times 2 times 3. So 1/3 is X, and the inverse of 1/3 would be 3. Another example, if I want to pick the element 7, 7 times 2 times 1/7, which in this case is 2. It works out for our star that the conjugates are just equal to my element because it is a commutative group. But that may not always be true. Let's let H be some subgroup of my group G. We will then say H is a normal subgroup of my group G if it is closed with respect to conjugates. So what that means, for any element A in my subgroup H, and any element X in my group G, so it doesn't have to be an element of the subgroup, just any element of the group, then we must have that XA X inverse is still in the subgroup. It doesn't have to be the same element, but it does need to still be in the subgroup. Let's let F going from G to H be a homomorphism. I want to prove that the kernel is then a normal subgroup of G. So the first thing I actually need to show is that this is a subgroup in the first place. I've talked about the kernel in a previous video, but I never proved it was an actual subgroup of my group. Let's start with two elements in the kernel, A and B. Well then, f of AB, since this is a homomorphism, is f of A, f of B. Since A is in the kernel, we know that f of A is the identity. Same thing with B. B is in the kernel, so f of B is the identity. And the identity times the identity is the identity. So that tells me that AB is in the kernel. So it is closed under the group operation. We also know that f of A inverse is equal to f of A inverse. We know that f of A is the identity, since A is in the kernel, and the inverse of the identity is the identity. So that tells me that A inverse is also in the kernel if A is. So this is a subgroup. Now that we have it's a subgroup, I need to prove it's a normal subgroup. So let's take an element of the kernel, the thing I'm claiming is a normal subgroup, and an element of my group. So I need to look at XA X inverse, and I need to show this is also in the kernel. So we're going to have f of XA X inverse. Using the property of a homomorphism, this is f of X, f of A, f of X inverse. I know that f of A is the identity by definition of the fact that A is in the kernel. So this is the same thing as f of X inverse, which we know is the identity. So this tells me that XA X inverse is also in the kernel, so it is closed under conjugates. So the kernel is in fact a normal subgroup. I'm also going to show that the range of F is a subgroup. Not necessarily a normal subgroup, but it is a subgroup. This time we're talking about the range, so it needs to be a subgroup of H rather than G. I'm going to denote the range by this RAN of F, so I'm going to pick two elements in the range, f of A, f of B. I need to show that if I multiply them, I'm still in the range. Well, my property of homomorphism says this is f of AB, which tells me that yes, it is also in the range, since now I have f of something, which is exactly the format for the range. We also need to look at f of A inverse. We've already proven in a previous video this is the same thing as f of A inverse. So that shows me that I'm closed under the inverses. So the range of a homomorphism is a subgroup of H. Let's do an example of a normal subgroup. Let's consider the group S3. So that consists of the identity, the element 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. A3 consists of the identity, 1, 2, 3, and 1, 3, 2. So I need to pick elements in S3, find their conjugates in A3, and see if it's still in A3. So if I let A, my element A, be equal to the identity, then yes, this is obviously going to work, since anything times the identity is itself, x times the identity would be x, and then xx inverse would still be the identity, which is still in my subgroup A3. And I'm not going to show all of these, but I do want to show a few of them. Let's start with 1, 2. For my element x, I'm going to let A be my element 1, 2, 3. And then x inverse would be 2, 1. If I work this out, we see that 1 maps to 2 and 2 maps to 3, so 1 maps to 3. 3 maps to 2 and 2 maps to 1. 3 maps to 1 and 1 maps to 2, so 3 maps to 2. And then 2 maps to 1, 1 maps to 2, and 2 maps to 1, so 2 maps to 1. So this is not equal to A, but it still does belong in A3. If I were to do 2, 3, times, this time let's do 1, 3, 2, times the inverse, which would be 3, 2. We have that 1 maps to 3 and 3 maps to 2. 2 maps to 3, 3 maps to 2, and 2 maps to 3. 3 maps to 2, 2 maps to 1. And we can see that this is still in A3. And you could check all of these possible products. I only did 2 here. We would still need to check 1, 3, and 1, 2, 3, 2, 3, and 1, 2, 3, 1, 2, and 1, 3, 2, and 1, 3, and 1, 3, 2. But you can check those to see that, yes, this would be a normal subgroup. Because if I pick an element in G times an element in my subgroup times the inverse of that first element, I am still in the subgroup.